Today we are breaking down BayesianVLA, Bayesian Decomposition of Vision Language Action Models via Latent Action Queries by Shiji Lian, Binyu, and their colleagues.
Yeah, and this one really gets into a critical flaw in how we're training robots right now. They call it the vision shortcut.
The vision shortcut. So what is that?
Well, basically, in most of our data sets, the visual scene, like seeing a toaster, almost perfectly predicts the instruction, which is put bread in the toaster. So the model just learns to ignore the language entirely.
Ah, okay. So the information from the language just collapses.
It collapses to zero. And BayesianVLA is their proposed fix. It uses a Bayesian decomposition, splitting the policy into a vision-only part and a language and vision part.
And it forces the model to actually listen.
Exactly. It optimizes something called the log likelihood ratio, which basically maximizes the mutual information between the action and the instruction. It can't cheat anymore.
How do they do that architecturally?
They use these things called latent action queries and a clever dual-branch training setup. And the results are, well, they're pretty significant. We're talking state-of-the-art on SimplerEnv and RoboCasa with an 11.3% jump in generalization.
All without needing new data.
All without new data.
Okay, that's the summary. Let's really dig in because this paper is, it's basically accusing some of the biggest models out there of, well, cheating.
It is. And they come with receipts. It's
Yeah.
backed by some pretty damning math and experiments.
So this vision shortcut, is it fair to say it's like a student cramming for a test by just memorizing the answers, not the concepts?
That is the perfect analogy, yeah. Imagine the teacher accidentally prints the answers in bold right next to the question. You just stop reading the questions entirely.
You just circle the bold text.
Right. And here the bold text is the visual scene. The data we collect is just too clean. If a human demonstrator sees a dirty sponge, they pick it up. If they see a cabinet, they open it. The environment, the dollars, just dictates the action. A dollar.
And the language instruction, $, just becomes background noise.
It's completely redundant. The authors formalize this with information theory, arguing that the conditional entropy approaches zero.
Meaning if I see the pixels, I can guess the text almost perfectly.
Exactly. And because of that, the model learns it can get a super low training loss just by looking at the image and completely ignoring the text tokens. It short-circuits the language part of its brain.
Now, this is usually just a hypothesis, right? But these authors, they really went for it. They proved it with what I think is one of the best gotcha experiments I've seen in a paper recently.
Oh yeah, the masked language experiment, it is just brutal.
Walk us through that one.
So they take a really strong baseline, Quengori 0T, which is a standard vision language action model. They train it normally. Then they train a second version where they literally just mask out the language. They completely blind the model to the text instructions.
So you have a vision-only robot.
Precisely. And they test both on the RoboCasa benchmark. The standard model, the one that could read, gets a 47.8% success rate. The vision-only one, which is just guessing based on the scene, what do you think it got?
I'm guessing it's uncomfortably close.
44.6%.
Wow. That's within the margin of error. It's the same.
It's basically the same. It proves that for most of these tasks, the language was doing almost nothing. The model's just overfitting to the furniture.
So we're pouring all this compute into these huge multimodal models.
Yeah, and they're just pattern matching the background. And the paper shows why that's so dangerous with their second experiment on the Libero Gold dataset. That one is designed to be ambiguous.
Ambiguous how?
Well, think of a scene with a bowl, a stove, and a drawer. If I just show you that image, you have no idea what to do.
Right. Put the bowl on the stove, the lure.
Exactly. The visual information isn't enough. You have to read the instruction.
Yeah.
And in that scenario, the vision-only model just completely fell apart.
What happened?
It went from a 98% success rate on the easy stuff down to just 9.8%.
Ouch. So it just stood there, guessing randomly.
Pretty much. Or it defaulted to whatever action was most common in the training data. This is the proof. The shortcut works until the moment you actually need the robot to listen.
And this must be why they fail so badly out of distribution. If the model just memorizes this specific kitchen counter texture means move left, then if you just change the lighting.
Everything breaks.
Yeah.
They showed that too.
Yeah.
They trained on Bridge Data V2 and tested on SimplerEnv. The vision-only model got a great training loss and 0% success on the test set. Zero. It learned nothing semantic. It just learned the lighting in the lab.
Okay, the diagnosis is clear. Our robots are ignoring us. So how does BayesianVLA fix this?
By forcing instruction following with math. They go back to the optimal policy equation and just apply Bayes' rule.
This is where they decompose the policy.
Right. Instead of just learning that directly, they split it into two pieces. A prior and a likelihood.
Okay, let's break that down. The prior is P-overs.
Which is basically the robot's habit. What action is likely, given only what you see?
And the likelihood is PLAV.
And this is the magic trick. This part asks, given the action I'm taking in this scene, how well does it explain the instruction?
So you're not just telling the robot to act, you're telling it to act in a way that proves it understood the command.
Yes. And their training objective is built around that idea. They maximize the log likelihood ratio, or LLR. The formula is basically log PLAVLV minus log PLV.
That subtraction is everything, isn't it?
It's the whole game. They subtract the obviousness. If the command is already super obvious from the scene, then PLV is high, and the model gets very little reward for doing the obvious thing.
It penalizes the shortcut.
It forces the model to find an action that provides new information about the command. It maximizes what's called the Pointwise Mutual Information.
It's like telling the robot, don't just do what looks right. Do the one thing that proves you are listening to me.
That's a great way to put it. Now, you can't just write that on a whiteboard and have the model learn it. They needed a specific architecture for this.
Which brings us to these latent action queries.
Right. So models like GR0T or BayesianVLA, they feed, everything into the action head. All the vision tokens, all the language tokens. It's a fire hose of data.
And super expensive computationally.
Exactly. BayesianVLA creates a bottleneck. They introduce 64 learnable tokens. They call them TIGALAR. And these KELAR tokens are the only thing the action head listens to.
So the diffusion model that generates the actions only sees these 64 query tokens.
Only their hidden states. It drops the complexity from being quadratic in the number of vision tokens, which can be thousands, to being quadratic in just 64.
Super efficient. But how does that connect back to the Bayesian math?
It enables what they call a dual-branch training strategy. This is the really clever part. They train two paths through the model at the same time with shared weights.
The priori branch and the posteriori branch.
Right. So branch one, the priori branch, gets an input sequence like this, vision, then queries, then language, VELers, Q2.
Okay.
But these are decoder-only models with causal masking. They can only see what came before. So in that sequence, the queries, QDeliver, can see the vision, $5.
But they can't see the language.
Exactly. So this branch is forced to learn the vision only prior. It has to guess the action without the command.
And branch two, the posteriori branch.
You just flip the order. The sequence is vision, language, queries, $5, QDeliver.
So now the queries see everything.
Now they see everything. That branch learns the true policy, and the LLR loss function is just a comparison between the outputs of these two branches. It tries to maximize the probability of the language given the posterior queries, minus the probability given the prior queries.
Wow, so it's explicitly training the model to value the difference between knowing the command and not knowing it.
That's it. And there's a key detail for anyone implementing this. They use a stop gradient on the prior branch. They don't want to make the vision-only model worse to increase the gap. They only want to make the language-aware model better.
That's smart. And what about at test time? Is it slower?
No.
Oh.
That's the best part. At inference, you just run the posteriori branch, so you get all this robustness with zero extra computational cost at deployment.
Okay, the theory is solid. Let's get to the numbers. Does this actually make better robots?
It really does. The results are very strong. On SimplerEnv, which is that tough out-of-distribution benchmark, BayesianVLA hit a 66.5% average success rate.
And the constraint it was compared against?
The direct comparison, QuenGeo0T, using the standard training, was at 55.2%. That's an 11.3% absolute improvement. In robotics, that's a massive leap.
Are there specific tasks where it really pulled ahead?
Oh, yeah, and they're exactly the ones you'd hope for. Put carrot on plate, saw a 13.6% jump. Put eggplant in a yellow basket, went up by 15%.
That yellow basket example is the killer, right? A vision-only model just sees basket. It ignores the adjective.
Of course. But BayesianVLA had to ground the word yellow to succeed. See the same thing on RoboCasa. There's a task, pick and place novel from placemat to plate. The vision-only model gets 34%. Standard training gets 48%. BayesianVLA jumps to 70%.
From 48 to 70, that's the difference between a demo and a reliable product.
It's a different class of performance, and they did a proper ablation study to make sure it wasn't just the latent action queries architecture giving them the win.
Because that's a decent architectural change on its own.
It is, and just adding the queries helped a little, maybe 2%, but adding the full Bayesian objective on top of that is what gave them the extra 6% boost. The theory is doing the heavy lifting.
I want to shift to what I think is maybe the most profound part of this paper, especially for anyone thinking about AGI. It's what I call the zombie robot problem.
Yeah, or what the field calls catastrophic forgetting.
Zombie robot is catchier. We start with these amazing foundation models, right? Models that can write poetry and solve calculus problems.
Incredibly capable general reasoning engines.
And then we fine-tune them on robot data to pick up a block, and they suddenly become, well, stupid.
The paper has a devastating example. They prompt the baseline Quingor0T model with a simple calculus problem, find the equation of a tangent line.
A high school math problem.
And the model starts out, it starts explaining derivatives, and then it just snaps. It starts repeating the word dentistry over and over again.
Dentistry, dentistry, dentistry.
Or it just devolves into random Chinese characters. Complete gibberish. The fine-tuning process is essentially lobotomize the model.
Why does that happen? Why does learning to move an arm destroy the ability to reason?
Because in standard VLA training, the language tokens are just treated as input signals, like pixels. The model learns to map them to motor commands, not to understand them as semantic concepts.
So the word tangent stops meaning a mathematical idea and starts meaning rotate joint 3 by 45 degrees.
You've got it. The semantic integrity of the language model just falls apart. But, and this is the huge win, BayesianVLA doesn't have this problem.
Why not? The LLR objective again.
Exactly. Remember, the objective is to maximize PLA-VLA. It forces the model to predict the language tokens from its own actions.
So it has to keep its language generation abilities intact.
It acts as a powerful regularizer. The language head has to stay healthy because the model needs it to explain its actions. So when they gave the BayesianVLA model the same calculus problem, it solved it flawlessly.
It preserved the foundation in the foundation model.
It did. And you can see why this is so critical. If we want robots in our homes that can not only do our chores, but also, say, explain why they sorted the laundry a certain way, we can't afford to destroy their reasoning centers during training.
We need them to be able to think.
We do. And this paper strongly suggests the Bayesian path might be the only way to get there without breaking the very intelligence we're trying to embody.
Okay, let's zoom out. What does this mean for the field going forward? The authors had some thoughts on data collection.
Yeah, they argue we need to completely rethink it. If we keep making these sterile, clean data sets where vision perfectly predicts the action, we're just feeding the beast. We're encouraging the vision shortcut.
We're training our models to be lazy.
Exactly. We need ambiguous data. We need messy scenes. We need videos of humans in cluttered kitchens hesitating, looking around, where you can't tell what they're about to do just by looking.
They mentioned using human video data sets.
Right, things like in and on or FizzBrain. Human life is naturally ambiguous. And ironically, that messiness is exactly what the models need to learn to actually follow instructions.
If the answer is obvious, you learn nothing. If you're confused, you have to think.
That's the core idea. They also briefly connected this to world models.
How does that fit in?
Well, BayesianVLA grounds language in the current action. World models try to ground language in a predicted future. You can see it as another kind of Bayesian inference.
If I imagine the toast is done, what action got me to that future state?
Precisely. And the authors hint that combining these two approaches could be a powerful next step grounding language in both actions and their imagined consequences.
That feels much closer to how people plan.
It really does.
Before we wrap, I just want to touch on the efficiency point one more time. That OK2$ complexity from the latent action queries, why is that such a big deal for engineers right now?
Because the amount of visual data is exploding. We have higher resolution cameras, multiple camera views, longer action histories. If your action decoder has to attend to every single token from 4K cameras over a 10-second window,
your robot will be thinking for a minute before it decides to move.
and you can't run it in real time. Compressing all that down to 64 query tokens first is a massive optimization. It lets you scale up your vision system without bottlenecking your control loop.
So, to sum it up, it performs better, it generalizes better, it saves the LLM's brain from being destroyed, and it's computationally cheaper at inference. This seems like a grand slam.
It really is a very complete solution to a very fundamental problem.
So, for our listeners, what's the big takeaway? If you're out there training a robot policy today, what's the one thing you should do after listening to this?
Run the masked language sanity check.
What's that again?
Take your best model, literally mask out the text instructions, and run your evaluation. If your success rate doesn't crater, your model isn't listening to you. It's just memorizing your lab setup.
That is a terrifying but necessary experiment to run.
And maybe stop trusting that your training loss going down means you're making progress. It might just mean your model found the easiest shortcut.
It's a real reality check for the field. We've been thinking we're solving tasks when maybe we've just been building incredibly overfit seam reactors.
Building very, very smart rocks. But this paper points a path toward actual grounded understanding.
Well, this has been fantastic. BayesianVLA, breaking the vision shortcut. A huge thank you to Shijilian, Binyu, and the whole team for this work. It feels like a really important course correction. Thanks, everyone, for tuning in. I'm now going to go ask my vacuum cleaner a calculus question and see if it starts screaming about dentistry.
Let me know how that goes.
Catch you all in the next one.